Boom! 2,000 pounds of iron falling 3 feet onto white-hot steel. The sound isn't a clang, it's a detonation. A pressure wave that hits your chest before it reaches your ears, that shakes dust from the rafters, that makes the water in the quench trough ripple outward from the center in concentric circles that break against the stone sides like waves hitting a harbor wall. If the raw power of the machines that forged the modern world speaks to you, subscribe now. This hammer could crack an egg or shape a warship, and you're about to see both. But that's the machine. Before the machine, there are the men. 8 of them, standing in a circle around an anvil, each holding a sledgehammer, 12 pounds, ash handle, crosspeen head, and swinging in sequence. 1, 2, 3, 4, 5, 6, 7, 8. The count is everything. Miss the count, 2 hammers collide. Miss the count, a sledge hits the man opposite instead of the iron. Miss the count, and the forging, a paddle shaft for a steamship, white hot, requiring 30 consecutive strikes to shape a single section, develops a cold spot where the hammer missed. Tobias Rane calls the count. He's been calling the count at the Bridgewater Foundry for 25 years, since he was 19. Since his arms were thin and his hearing worked in both ears and the forge fire hadn't yet baked the left side of his face into a permanent squint. He stands closest to the workpiece. His hammer falls on the one, the master stroke, the heaviest blow, the one that sets the metal's direction. The 7 other men follow, their hammers falling in descending force. 2 and 3 are nearly as hard as 1. 6, 7, and 8 are shaping blows, lighter, guiding the metal into its final position before the whole sequence repeats. You don't hit the iron, you convince it. The heat makes it willing. At white heat, iron is soft, malleable, eager to move. At red heat, it resists. At black heat, it cracks. The window between willing and resistant is a matter of minutes. 4 minutes at white heat. Maybe 5 if the forge is hot enough and the iron mass is large enough to hold its temperature. In those 4 minutes, Tobias must complete every shaping blow, every correction, every adjustment that the section requires. After 4 minutes, the iron goes back in the forge. Wait for white heat. Start again. The paddle shaft they're forging is for a steamship. 3,000 pounds of wrought iron, 18 feet long, 6 inches in diameter. It must be forged from a single billet. No welds, no joints, no seams where stress could concentrate and fracture under the rotational load of a ship's paddle wheel. A single billet means heating one section at a time, forging that section, moving to the next, and repeating until the shaft is complete. Estimated time, 3 weeks. Estimated hammer blows, 30,000. Tobias calls the count. His men swing. The iron moves. And Tobias knows, has known for months, that the industry is outgrowing his hammer. The shafts are getting bigger. The axles are getting heavier. The marine engines are demanding forgings that 8 men with sledgehammers cannot produce in any reasonable time. A propeller shaft for Brunel's latest ship would require a forging team of 20 men swinging together, a number too large to coordinate, a rhythm too complex to maintain. James Nasmyth arrives at the Bridgewater Foundry in the autumn of 1839. He's 31, Scottish, an engineer with an artist's eye and an inventor's impatience. He watches Tobias's team forge the paddle shaft, watches the count, the coordination, the physical exhaustion of 8 men swinging 12-pound hammers in sequence for 30 minutes before rotating out for the next shift. He watches the forging, the iron moving under the hammers, slowly, incrementally, shaped by human force at the limit of human endurance.
The force is right. The control is right. The men are wrong. Not wrong, limited. The men are limited, not by skill, but by physics. Muscle generates force linearly. Steam generates force exponentially. If you replace the men's arms with a piston...
He opens his sketchbook. Page 41. Draws a rectangle, the hammerhead, a vertical line, the guide rails, a circle at the top, the steam piston, and an arrow pointing down, the direction of the blow. The sketch takes 90 seconds. It's the simplest drawing that will change the forging industry. A 2-ton block of iron, raised by steam, guided by rails, dropped with gravity and steam pressure onto an anvil. The hammer takes 4 months to build. The frame, cast iron, 2 vertical pillars connected by a crosshead, the structure that supports the piston and guides the hammer block. The toop, the hammerhead, a 2-ton block of cast iron, machined flat on the striking face, attached to the piston rod. The anvil, 20 tons of cast iron, sunk 6 feet into a foundation of oak beams and compacted earth, the mass that absorbs the blow. The steam cylinder sits at the top. Nasmyth's innovation. The same piston that raises the top can also drive it down, adding steam force to gravity. In gravity mode, the top falls freely, 2 tons falling 3 feet, a gentle blow by forge standards. In steam mode, the piston drives the top downward with the full pressure of the boiler, a blow that could flatten a horse. First test, February 1840. The boiler is fired, steam raised. Nasmyth at the valve, a brass lever that controlled steam admission to the cylinder. Tobias and his men at the gallery, watching. The anvil is empty, no workpiece. This is a test of the mechanism, not the forging. Nasmyth opens the valve, full steam. The piston drives the top upward. 2 tons of iron rising 3 feet in under a second, the guide rails vibrating with the force. At the top of the stroke, Nasmyth reverses the valve, full steam downward. The top falls, not falls, fires. 2 tons accelerated by gravity and steam pressure, striking the anvil with a force that... The building shakes. Not the anvil, not the floor. The building. The brick walls vibrate. Dust falls from the roof timbers. The water in the quench trough, 20 feet from the hammer, doesn't ripple. It jumps. A tool rack on the far wall crashes to the floor. And the anvil, 20 tons of iron on an oak foundation, shifts. 1 inch. The most massive single casting in the foundry moves under the blow. Silence. Then Nasmyth, surveying the cracked floor tiles around the anvil base.
Well, we know it works.
You've also cracked every tile in the building.
Those tiles were poorly made.
The problem isn't power. The hammer has power, vastly more than 8 men with sledgehammers, more than any forging tool in existence. The problem is control. Full steam, full drop. The blow is devastating, but indiscriminate. It would shape a shaft by deforming it beyond repair. What Tobias does with the hand hammer, the graduated force, the heavy strike followed by the shaping stroke, the precise application of exactly the force the iron needs, the steam hammer cannot do. It has 2 settings, off and catastrophe. Tobias watches the demonstration with the particular expression of a man whose expertise has just been simultaneously threatened and validated. The hammer needs what he has: judgment, the ability to read the iron and choose the force. Without him, the hammer is a 2-ton brick falling on an anvil. With him, with his knowledge of when to hit hard and when to touch, the hammer could be... He doesn't finish the thought. Not yet. The hammer needs a different valve, a valve that allows partial steam admission. Not full open or full closed, but every graduation between. A valve that lets the operator choose the force of each blow individually, from featherlight to full power, with the precision of a hand hammer forger choosing between a tap and a strike.
It's not the hammer that's wrong, it's the valve. You've given it one note. I need an octave.
3 months. Nasmyth redesigns the valve, a rotary mechanism with variable steam admission, allowing the operator to control the force of each blow from 1/10 to full. The tup can now be raised 1 inch, a gentle tap, or 3 feet, a full strike, and everything between. The operator, sitting at the valve lever, watching the workpiece on the anvil, chooses the force the way Tobias chooses his hammer weight, by reading the iron. Tobias learns to operate the hammer. Not happily. The transition from hand hammer to steam valve feels like a demotion, like exchanging a sword for a lever, like replacing the direct physical connection between smith and iron with a mechanism that intervenes between intention and action. But the mechanism is precise, more precise than his arm. The valve allows force adjustments of 50 pounds, finer than the difference between his lightest and second lightest hand hammer blow. He starts with a test piece, a bar of wrought iron, heated to white, placed on the anvil. He opens the valve. Partial steam. The tup rises 1 foot, falls, strikes the iron with a controlled blow. 300 pounds, equivalent to a journeyman's full swing. The iron moves, obediently, predictably. The tup rises again, 1 foot, falls, 300 pounds. The iron moves the same distance, the same direction. Consistent. Every blow identical. No variation for fatigue, for timing, for the 100 small muscular inconsistencies that make hand forging an art instead of a science. A 2-ton hammer that can crack an egg without breaking the glass beneath it. If that sounds impossible, subscribe. You're about to watch it happen. Erskine Voss visits. The rival foundry owner. Soft hands, waistcoat in the forge, the appearance of a man who sees labor as a cost to be minimized. He watches the hammer, watches Tobias at the valve, sees the potential not for craftsmanship, but for replacement.
So, 1 man and a machine, instead of 8 men and sledgehammers.
1 skilled man and a machine. The valve requires judgment.
Any man can turn a valve.
Any man can hold a paintbrush. Not every man can paint.
Voss is right about the economics, wrong about the skill. The steam hammer does replace the team of 8 hand hammer men. It replaces their force, the physical labor that human arms provide. It does not replace their knowledge, the understanding of iron, of heat, of timing, of force application that separates a forgeman from a laborer. The hammer needs an operator who knows iron, who can read a white-hot billet and know that this section needs 600 pounds, and that section needs 200, and the transition between them needs 3 blows of increasing force at 30-second intervals to avoid the thermal stress that causes cold cracking. Khan, Tobias's nephew, 19, who has been watching with the particular fascination of a young man who sees technology as liberation rather than threat, asks to try the valve. Tobias lets him. The boy is careful, tentative, his blows too light, fear of the machine's power, overcorrecting for the first test's devastation. Tobias adjusts his hand on the valve, shows him the resistance point, the position where the valve wants to rest, the equilibrium between open and closed. Feel that? He says. That's where the hammer tells you it's ready. The demonstration is Tobias's idea, not Nasmyth's. Nasmyth wants to demonstrate the hammer by forging a shaft, which is dramatic but expected. Tobias wants to demonstrate something else. Not power, control. The absolute, infinitesimal, impossibly precise control that the variable valve gives to a skilled operator. A wineglass, crystal, placed on the anvil, the 20-ton anvil, the massive iron that absorbed the blow that cracked every tile in the building. In the glass, a raw hen's egg, brown shell, 2 ounces, the most fragile object in the foundry, sitting on the most massive, receiving the blow of the most powerful machine ever built for metalworking. The gallery is full. Nasmyth has invited engineers, foundry owners, members of parliament, newspaper correspondents. They've seen the hammer forge, watched Tobias shape a 200-pound billet into a crankshaft journal in 12 minutes, work that would take his team of 8 men 4 hours. They're impressed by the power. Now they'll see the precision. Tobias stands at the valve. He doesn't look at the gallery. He looks at the egg, reads the object the way he reads iron, its weight, its fragility, its tolerance for force. An eggshell cracks at approximately 4 pounds of force. The wineglass breaks at approximately 15 pounds. The difference, the window between cracking the egg and destroying the glass, is 11 pounds. 11 pounds delivered by a machine that can generate 200,000. He opens the valve. The slightest turn, barely a degree of rotation. Steam enters the cylinder. The top rises. 1 inch. Less than 1 inch, half an inch maybe, a movement so small that the gallery can barely see it. The top hangs at the top of its half-inch stroke. Tobias's hand on the valve is steady. His breathing is steady. His deaf ear is toward the gallery. His good ear is toward the hammer. He's listening to the machine. He closes the valve. The top falls. Half an inch. 2,000 pounds of iron falling half an inch under gravity alone. No steam assist, just the weight of the block and the pull of the earth. The strike force, approximately 6 pounds, delivered across the tup's flat face, concentrated on the eggshell by the egg's own geometry. Tick! Not a boom, not a clang, a tick. The sound of 2,000 pounds of iron touching a 2-ounce egg at the precise force required to fracture the shell without accelerating through it. The gallery is silent. Tobias raises the top. Half an inch. The glass is intact. The egg is cracked. A neat fracture running across the crown. The shell compressed by exactly the width of a pencil line. The yolk is visible through the crack, unbroken. Nasmyth hands the wineglass. Egg still inside, shell still cracked, yolk still intact, to a parliamentary observer. The man takes it. His hand shakes. He nearly drops it. The glass wobbles. Nasmyth catches it.
The hammer used 2 tons of force to crack the egg. You've nearly used gravity.
The observer does not drop the glass. But the point is made, and the real point is not the egg. The real point is that a machine designed to forge ship shafts can crack an eggshell at 4 pounds of force. That the same tool that shapes industry can also perform surgery. That control isn't the absence of power, it's the mastery of power. And the mastery belongs to the man at the valve. Tobias retrieves his sledgehammer from the wall. Not to use it. The steam hammer does what 8 men with sledgehammers cannot. But the hand hammer still has work. Finishing work. The fine adjustments, the surface corrections, the last few taps that smooth a forging after the steam hammer has completed the heavy shaping. The machine does 95%. The man does the final 5%. And the final 5% is where the craft lives. The fingerprint of the smith on the surface of the iron. The difference between a forging and a good forging. Nasmyth's steam hammer enters production in 1843. Within 10 years, every major foundry in Britain, France, Germany, and the United States installs one. The forgemen who operate them are the highest paid men in the heavy engineering trade, not despite the machine, but because of it. The machine amplifies skill. It doesn't replace it. A forgeman with a steam hammer produces in 1 hour what a team of 8 produces in a day, with greater precision, less waste, and, Tobias would note with grim satisfaction, less damage to the operator's hearing. The egg-in-the-wineglass becomes the most famous demonstration in Victorian engineering. It travels from workshop to workshop, from foundry to foundry, from trade show to parliament, as proof that the Industrial Revolution isn't just about force, it's about control. The control of a man who learned to swing a sledgehammer and then learned something harder, to barely touch a valve and trust the machine to do what he asks. Not more, not less. Exactly. Sketchbook page 41. A rectangle, a line, a circle, an arrow. The simplest drawing, the most powerful machine. And a cracked egg in an unbroken glass sitting on an anvil that weighs 20 tons beneath a hammer that weighs 2, operated by a man whose hands, scarred, calloused, 25 years of forge work encoded in their grip, rested on a valve lever and chose the force of 4 pounds out of a possible 200,000.
That's not engineering. That's art.